Good evening. Thank you very much for being here in this new session of the Coffee Talks CIMNE. I'm glad to introduce Professor Rene Meziat. He is holder of a mathematician degree from the University of Los Andes, and he did his PhD here at the UPC. Over his career, he has been part of the faculty of several institutions like the Universidad de Castilla-La Mancha and also the Universidad de los Andes in Bogotá, Colombia. He has contributed to over 100 academic papers, and actually he has been a very good friend of CIMNE because we collaborate for a long time, and he started one of the CIMNE's joint lab in Bogotá. So, Rene, floor is yours.
Thank you, Francisco. It is a pleasure to be here. I'm very thankful to Rene, Francisco Zárate, and many professors and researchers here in CIMNE who have been colleagues and friends for several years. I did my PhD here in UPC in Barcelona. And I have worked for many years with the support and company and friendship of Eugenio and colleagues. So to me, it's a pleasure to be here, and it's an honor to be here. And it's a double honor contribute to one of the coffee talks in Sydney. I will speak about calculus of variations and some connections that exist with numerical methods, mainly with the finite element method. I will explain to you the mathematical background and the mathematical basis that support my research. This research has been done with the support of CIMNE and many other institutions in Colombia and here in Spain. And I will speak with some biased to several topics in applied and fundamental mathematics, but I will try to connect these theoretical facts with more practical and more applied problems, mainly in material science. To do this talk more easy and more understandable for many of the people in the audience, I will use my films, which are made in English and with a strong mathematical content, but I will alternate with this small digital blackboard, which allow me to explain in a more didactical way some of the concepts and some of the results that I want to share with you this afternoon. Thank you very much. I will start my talk. This talk, or the content of this talk, is shared with Juan Manuel Rodriguez. Juan Manuel is now working in Medellin, in the EAFIT University. I am working now in the Universidad de los Andes in Bogotá. This is a joint work. This is the content of a paperwork that we expect to publish very soon. Well, this is the abstract, but as I told you, I will try to convert this strong mathematics in more understandable concepts, mainly concepts that are very used and are very common in materials engineering. Well, what you can see here in this slide is a classical, very typical variational problem as we use and as we understand in mathematics and physics. The expression inside the functional is called Lagrangian, but in this case, it is motivated by the classical problem of one-dimensional linear and nonlinear elasticity. I am following with the pointer, this expression. This expression is split in two terms, and inside the Lagrangian, inside the integrand of this integral, you can find a very well-known function, admissible function called u. This u is the elongation, and many in physics and many in call this u in this way, the elongation. The derivative of the elongation is the deformation, the unitary deformation. So the first expression on the left is one expression that measure in some way the cost of the deformation energy. And this function called C, this Greek C, represents the potential of internal deformation on the body. And this body is a very, very, very simple body, which occupies a one-dimensional interval starting from I to B. And the second term is also well known in engineering, and this term amounts for the charge, the forces, the external forces that you can apply to this material or to this one-dimensional body. So at last, all these functional accounts for the total energy into the material. The first term is the internal energy according to the formation energy and according to the internal behavior of the material, and the second term accounts for the external charge, external actions into the body. What is my interest, what is new, and what is interesting in this problem? To me, as a mathematician, I have been working in this kind of problem for several years. My interest is what happens when the left term is a nonlinear term and a non-convex term. Remember that in engineering, this potential energy usually is a parabola, and it is convex, and it is very well known in physics, engineering, and mathematics. But my concern is what happens when this term is not convex and is not a parabola, and how can we treat this problem with different alternatives and different mathematical tools for solving this problem in this case, when the first term is not convex, and of course the material is not in the linear regime. I mean, in engineering terms, what I am studying here is what happens when the material is forced very strong in such way that you go further than the elastic regime. And this is very interesting for many designs. I mean, this is very interesting for physicians, and it's very interesting to me as a mathematician. Well, the overview of this talk is very, very, very extensive, and it includes many, many classical and many recent and developments in pure and applied mathematics. Pure and applied mathematics. Well, we have been successful working this problem in a particular case that is very important for application, but it's very important for me as a mathematician because I'm working in the case when this nonlinear expression can be expressed as a rational function. So, as a mathematician and as an applied mathematician, I can use a lot of curves, a lot of nonlinear potentials that can be expressed as a rational function. Many years ago, let's to say more or less 10 years, I studied this same problem, but using polynomials. But polynomials are not so well adapted to represent practical curves taken from data. Remember that this curve is the classical energy deformation linked with the internal nature of many materials. So when we are interested in taking data from experimental tests, so we are a bit constrained if we only use polynomials. When I realized that I could use rational functions, I be very happy because by using rational functions, I'm free to modulate many interesting real curves called deformation energy taken from many different materials. Well, the other mathematical feature in this expression is that this rational function can change depending from this point of view. I could simulate and I could modulate and I could solve many problems in which for every physical point in the domain, I can use a different rational function. That's very important for applications because, as you know, the features of the material change in every point of the material. Or in other words, the features of the material may change along the length of the material. That's very important for modeling, and that's very important to me as a mathematician. As you well know, from a mathematical point of view, a rational function is the division of two polynomials, and I am completely free to use information energy potential, I will investigate where into the formation of the body this internal potential is not convex, and I will analyze this with this mathematical object called A sub x. What it means A sub x? Well, it's very simple. It's only the set where the internal energy potential is not convex according to different levels of deformation. I mean, many energy potentials are convex for low levels of deformation, but they can be not convex in higher levels of deformation. So I need this, but I treat as a mathematical object, I treat as a set. No more than that. Well, this is the equation 9 is a very famous, well-known result in variational analysis, in convex analysis, in optimization, and calculus of variation, that when you use the convexification of an optimization problem, the convexification of the problem is going to provide the same minimizer that the original problem, in spite of the fact that the original problem were or was not convex. This is a strong result, and it is well known from the middle of the 20th century, and it was proved by many people involved in calculus of variations. Well, then I need some technical requirements. I will not stop on them. And these technical requirements are about the shape of the deformation energy potential. Remember that always the deformation energy potential is this Greek letter called C. Okay. Okay. Well, this is the mathematical way in which I can express some of my results, because I have discovered, or I have proved, that these kind of problems have a solution in the Sobolev space that I mentioned before, when we can certify, or when we can observe the connection between the external forces. Remember that H were connected with external forces into the material. And here, this is a very easy geometrical operation. It can be expressed with terms taken from calculus, but it is very geometrical. What I am doing here is first use the convexification of the potential of the deformation energy, and then take the first derivative in the deformation. This expression has some geometrical meaning, but at last, what I stress here, or what I am stressing here, is that if I can connect this geometrical expression taken from the potential energy, and if I could connect in this way with the external forces, then I will be sure, and I am proving, that the original non-convex, non-linear variational problem is going to have a solution in the same Sobolev space that I showed to you some minutes ago. Well, what happens with the non-convexity? What happens with the non-convexity? Well, the non-convexity for these kind of problems is a very hard problem. It's a very tricky problem, because from the mathematical point of view, these problems hasn't a solution, even in this Sobolev space. So what is the purpose of studying problems that lack of solution in the same solvable space that you are studying? Well, the point is that in spite of the fact that this problem lacks a solution, physically and from a point of view of engineering and design, the material and the design and the external forces that I apply to a particular material with this nonlinear behavior, the material is going to seek the lower energy value for the general function. I mean, in some way, in spite of the fact that from a mathematical point of view, this problem has not a solution, what has been observed experimentally and what we are completely sure that exists is that there are many functions that are decreasing this functional step by step, in spite of the fact that I won't converge to no classical function, but I will converge to a very important object in the applications and in the theoretical setting of this problem. I will explain. This equation, this formula may look a bit cumbersome, but I will explain what I am doing here. This is exactly the same nonlinear variational problem that I showed to you some minutes ago. But there is a very, very, very small difference. Instead of work with classical functions, I am working here with statistical variables. I am working here with probability distributions. This mu sub x is a probability distribution linked with the physical point x. Remember that I told to you that the features, the properties of the body may change along the body. Well, instead of work with a classical function, which is defined in every point of the body, I will work with a new, more creative mathematical object called adjunct measure. What is adjunct measure? Adjunct measure is also called a parameterized measure. What is a parameterized measure? A parameterized measure is a family of probability distributions parameterized, linked with every point x. In simple words, instead of working with a classical functions that take a point and return a value, I'm taking a new mathematical object called parameterized measure that takes a physical point and returns a probability measure, or more common call it a statistical variable. And what is this operation? This operation, from the point of view of the statistics, is very simple. This is a mean value. This is an average value. This is the average value of this probability measure integrated with this physical function called C. So I change the original non-convex nonlinear variational problem by this new, a bit strange variational problem, but define it in a new mathematical object called Young measure. What is the importance of this formulation? The importance of this formulation is that I will attain the minimum value of the original non-convex problem. Remember that I told to you that these kind of problems lack of solution into a classical Sobolev space. Then I will obtain, using tools from probability, the strategy that the material is going to take in order to decrease the value, the energetical value that is represented by the functional into the variational problem. So at last, I will show you that this problem indeed has a solution, but not a solution as a function. It has a solution in this new family of objects called Young measures, also called parameterized measures. Well, this is a more familiar, more easy way of express this kind of objects. For every point x into my body, I will associate one particular probability measure, or if you want, a statistical value. So in this way, many open problems in this modeling that is very difficult because we are talking about nonlinear materials are going to be more manageable and more easy to resolve. Well, this is the same problem now expressed with this family of Young measures, and instead of use a function that represents the deformation energy into the deformation potential, I will use a very simple statistical average by using the mean value of this function integrated against this probability distribution. Well, the next step is bring all this to a more classical setting in which I could work with well-known numerical methods. The key is work with moments. What are moments in the setting? Well, remember that every probability measure has a family of moments that we use to estimate different features of the probability distribution in probability and statistics. The essential idea is that instead of work with a very strange mathematical object called a Young measure, I will work with a more easy object that represents the moments, the algebraic moments of this probability measure. So in this way, I take this theoretical problem and I put it into a more affordable setting of numerical calculus and numerical methods. And I will forget for a moment many issues connected with this theoretical object called a Young measure or a problem setting. Well, our recent result is how to manage all this idea in the setting of rational functions. Well, in this, we have been successful working with Juan Manuel Rodriguez in Medellin, in the University, and we can apply this idea by using not the moments of the original measure, but we can do the same work by using the moments of the original measure transformed, changed into a new probability measure by doing this substitution. But notice that what I am doing here is to use the polynomial that appears in the denominator in the lower part of the division, so that instead of work with this function called mu sub x, which is a probability distribution, I will work with this other called mu sub x, which is also a probability distribution, but has been transformed by this very simple algebraic and mathematical operation. What we obtain is that I can formulate the original problem as a complete convex finite-dimensional optimization problem in which I represent the probability measures by their moments, not with the distribution, as is usually in probability or in statistics. What I do is use only the moments. And in this way, I can shrink this huge mathematical object in only a small vector, which is linked with every physical point called x. And this is more or less what we obtain. Instead of work with a probability distribution, I work with a small vector in into an Euclidean space with few dimensions. Well, we can put all this into a solver of convex optimization. There are many solvers of convex optimization. We used to develop solvers for convex optimization, and I devoted many years to create, to design, and to propose new algorithms for convex optimization, and we apply here to solve this kind of problems. Well, this is a technical issue. But for mathematicians as me, this is very stimulating, because this is the classical representation of a family of moments. What happens here is that to characterize a vector as a set of moments that came from a probability distribution, we need to impose a particular constraint, and this particular constraint means that this matrix must be positive, and this entails a convex set into the finite-dimensional Euclidean space in which we are trying to find the solution of the transformed problem into moments, not in probability measures, in moments. And we succeed doing this. Well, this is the classical characterization. There are many well-known mathematicians that have been working in this classical problem. It is a classical problem in mathematics. It is called the problem of moments, and there are many views. Usually, these kind of problems can be solved using model algebra. And this is what we obtain. My new formulation in moments, which is a finite-dimensional optimization problem, has the same minimum value that the original problem that lacks a solution. Please notice that on the right, I am talking about infimum, but on the left, I'm talking about minimum. From a mathematical point of view, are different concepts. The problem on the left has a solution. So this is why I could use the word minimum, but the problem on the right lack of solution. So I'm forced to use the word infimum. This is a very subtle mathematical concept, but very important. Well, I have been delighted using my tool to prove that many problems in this setting has solution in the original Sobolev space. But Rene, you told us some minutes ago that this problem lack of solution. That's right. I told you that this problem lack of solution, or may lack of solution. Well, what I have done as a mathematician is to prove that many, not all, many of these problems have a solution in the same Sobolev space. But what I did was go to the world of probability measures, put these measures into the representation of moments, and calculate with convex optimization and tools of convex analysis to prove that at last they had a solution. And this is my contribution as a mathematician. So, well, I have proven that many of these problems has a real particular solution in the Sobolev space. I will go fast through these theoretical results, and I will show you what I have found. My examples. Well, what is really new, or what is really important from a practical point of view, is not that this problem had a solution in a particular Sobolev space. What is very important is show to you that I am able to show that they have a solution and that this solution exists, but it's more important to show to you that I am able to calculate the solution by using a combination of the classical finite element method and tools taken from algebra and from probability to characterize this kind of moments. This is really new, and this is my contribution to the more applied interest or more applied scientist. Well, this is a typical case in which I'm sure, and I can prove mathematically, that this problem has a solution, but not this, that this is a highly nonlinear, highly non-convex variational problem. And this represents the behavior of a particular nonlinear material. Well, this is the general setting. In many general settings, I have proved theoretically that the problem has a particular solution into a particular Sobolev space. Well, this is the result. Now, I told you that I could transform the original problem into more theoretical problem based in probability measures, but I told you too that I could transform this problem into a particular convex finite-dimensional problem, which is more practical to be solved by using algorithms taken from optimization techniques. Well, this is a theoretical point, but which is very important from a practical point of view. This star means optimal. Usually we use stars like this to refer an object that is optimal into an optimization problem. But what is on the right side is a Dirac distribution. So what happens is that many of these problems reveals a solution in the way of a Dirac distribution. These Dirac distributions are very well known in physics, and I am using here to prove, this is my theoretical tool, to prove that these problems have a solution. Well, this is once again the setting in rational functions. This is once again the setting using moments instead of using probability distributions. Well, this is the classical formulation of the characterization of the moments for a set of values that for sure must be characterized as moments. And this is my original problem in your measures. Well, and finally, this is the problem, finite dimensional problem, as a complete finite dimensional problem in the setting of a convex program. Well, this is also the theorem that allows me to show that these problems are going to have a solution into a particular Sobolev space. Well, at last, we have attained the numerical way to solve these problems that originally it was supposed that they lack of solution, but we proved that they indeed have a solution. But now we can also estimate the minimizer by using finite element method, and that's what we do in this in this example. This is a very, very non-linear, non-convex problem in the U prime. Remember that in practical applications, U prime is the deformation. This is a integral double minima potential, which is highly non-convex and highly non-linear. And this is the technique that we have proposed, in which we transform the original problem in moments. We characterize these moments by the positivity of a particular matrix, and then we take into the finite element method by using a classical one-dimensional splines or two-dimensional splines, as you want, and then we can obtain the results by solving this problem with classical tools from complex optimization. And this is a particular numerical solution for this problem. And we can certify now, using numerical tools, that the original problem indeed has a solution. Well, this is the shape, the nonlinear, non-convex shape of this potential, so that you can see how nonlinear and how non-convex it is. This is another example using another nonlinear, non-convex potential that you can see in this figure. The other graphs are the values of the moments, because remember that the original functions is transformed into a probability function, and then is transformed into a vector, a small set of moments. So each one of these graphs is a graph of a particular moment to represent the original probability, which in turn represents the original nonlinear problem. Well, that's my contribution. I'm plenty. I'd like to answer your questions, and I would like to discuss this research. I have been researching in this slide for many years. I have received some support from CIMNE. I have been working with my students in Colombia and with other colleagues in Europe. I have some results with people working in Czech Republic. I have some results with people working here in Barcelona and others working in Spain. Thank you very much.
Thank you very much, Rene. Very nice talk. Thanks for lowering the level for the engineers like me. I don't know if there are any questions in the audience. Yeah, please.
Thank you very much. A very interesting talk. I'm not quite sure I followed all the subtleties in terms of the mathematics, but for what I could understand, being an engineer, you were replacing the U dash, the strains, by these Young's measures, and then the moments and so forth, and cleverly playing with that. As engineers, really the U dash, which is the strain, is one of the important things that we need to extract from the solution, because from that we find stresses and we'll find things that we need in order to decide and to compute. And you seem to have replaced them by other things. Can you then reconstruct, having found the solution, can you reconstruct and give us a strain so we can find stresses and the things that the engineers like to do?
Yes, I can. And what happens is that the nonlinear situation entails that the deformation may take two different energetical values. Every energetical values can appear into the material, so that in some parts of the material, the energetical value 1 may appear in one region. In other parts of the body, the other energetical value may also appear in other parts of the body. What is very interesting and what we grasp with this method is that the two energetical different values combine into the body, and we can find where into the body they will be combined and in what proportions will be combined. I will explain you in more practical terms. Remember, when you work with steel, some particular industrial steels may present two solid phases from a thermodynamical point of view. So the combination of these two solid phases entails physical phenomena like martensitic transformation and this kind of phenomena. So we can modulate and we can simulate and we can estimate in what proportions appears one solid phase into the material and the proportion that it represents compared with the other. Because the two proportions add to one, because are proportions, percentage. So me as a mathematician, I don't think these proportions like proportions. I don't think of these proportions as a thermodynamical situation. I think of them as probability distributions. In the same way that when you throw a coin, then you can obtain two results, 50-50% probabilities. I do exactly the same simulation, the same representation, so that into the body, the proportion where the two solid phases are combined, I represent this combination as a only probability measure. But this single probability measure may have only one value in the case of direct measures, but it can has two values, a bivariate probability. In this case, I can estimate, I can calculate, and I can conclude in what proportions will appear one of the solid phases and in what proportions are going to appear the other solid phase of this kind of steel. I like to show you a little sketch. May I?
Yeah.
Okay.
Very short, please.
What I am talking about is about this. Remember that a nonlinear behavior of nonlinear materials is something like this. Or I represent that something like this. This is a potential, an energy potential. And this is the formation. This is the formation. So when I draw the convexification of this nonlinear non-convex curve, this is one energetical level, and this is other energetical level. But what I am representing in the horizontal axis is the formation. So that this is a first deformation level that is associated with this energetical level. This other is another deformation level associated with another energetical level. But in the middle, the material stops in this energetical level. And the material is going to combine the energetical level A with the energetical level B. And this is a percentage and this is a percentage from a thermodynamical point of view. But this is what I call a Young measure, because I represent like a bivariate probability measure. I mean, this is a probability measure that has two events, A and B, and may have two probabilities. And each event is a thermodynamical stable state, like the case in two solid phases in steels.
Thank you very much.
Thank you for this support extra slide, which is very clarifies many aspects of the.
Any other
We
questions?
are working with non-convex problems all the time, and we just go through the convex region, you know.
Okay, well, I think we are running out of time. Thank you very much for your talk. Thanks for coming also. You know, you're always very welcome. And thanks all of you for being here and for your time. Thank you.